Hey everyone, in this video we are going to be talking about accuracy and precision. So first off, we need to talk about what does it mean to be accurate and what does it mean to be precise. So to be accurate means the closeness of a measurement to the true or accepted value. So basically what we're saying is, in order to be accurate, you have to be very close or the same as whatever your accepted value is. And you will be told what your accepted value is. And then to be precise describes the closeness of multiple measurements or its reproducibility. So what we mean by being precise is just, if I have all of my data or all of my numbers, how close are they to one another? So instead of being close to the actual value or the accepted value, we're just worried about, are they close to one another? And then talking about that accepted value, the accepted value is the value that all scientists in the field have agreed upon or that they consider it to be scientific fact. And again, you will always be told whatever the accepted value is. And just to recap, accuracy is how close you are to that accepted value. Precision is how close all of your data points or numbers are to one another. And so a really great way that we can think about this is by using a dartboard. So we are going to actually draw a dartboard, and then we're going to talk about the dartboard. So with our dartboard, we have our very center, which we all know is the bullseye. And then I'm going to draw two more circles around the bullseye. And again, they don't have to be perfect. Okay, so again, we know that the center is the bullseye. And typically, the bullseye is going to represent the actual or accepted value of what you are measuring. So just remember, bullseye, the center, and the reason why we can say that is because that's our goal, right? We're all trying to hit that bullseye. So that is going to be our accepted value. Okay, now we're going to add some points onto our dartboard. If you don't have colored pencils, that's okay. You can just do the shapes. If you do have colored pencils, it's very helpful to include color. But again, if you don't have access to that, that's okay. It just makes things a little bit easier. And you don't have to do the same colors that I'm doing, just as long as you have some shapes that you are able to recognize. And then we're going to put in some X's. Okay, so now we're going to first look at the red triangles. And if we look at the red triangles, first off, they are directly on that bullseye. So since they are directly on that bullseye or that accepted value, they are going to be accurate. And then in terms of precision, if I look here, they're all right beside each other. And since they're all right beside each other, they're also going to be precise. Okay? Now, let's look at our blue circles. So, our blue circles, they're pretty well accurate. And the reason why we're going to say that they're pretty well accurate is because they are close to the bullseye. Okay, so they're going to be accurate. But whenever I look at these circles, they are not close to one another. They are on opposite sides of the board almost, so they are not precise. Okay. Then we have our purple circles, or purple squares, and if we look at them, again, in terms of accuracy, they are not near the bullseye. They are over to the side, so they are not accurate. But in terms of precision, they are all right beside each other, so they are going to be precise. And then our last one is the green X's, and they are all over the board. They are nowhere near the bullseye, and they are nowhere near each other. They are literally everywhere. So that means that they are not accurate, and they are not precise. Okay, and again, that's just a visual way of looking at accuracy and precision, but for us, we're going to be looking at more word problems than we are necessarily pictures. So, our first example. The following measurements were made to determine the density of a material whose value was 3.75 grams per milliliter. And then we're given some data. So for trial number 1, $4.75. For trial number 2, $4.76. And trial number 3. Is 4. And then we are told to describe the accuracy and precision of the data above. Okay, so again, the following measurements were made to determine the density of a material whose value is 3.75 grams per milliliter. And then we're given data about the trials and asked to describe the accuracy and precision of the data above. Well, first things first is I've got to know what my actual or accepted value is. And in this case, my actual or accepted value is going to be this 3.75. So now, whenever I am thinking about this, if I look at 4.75, 4.76, and 4.74, they are nowhere near 3.75. So that means that this is going to be not accurate. In terms of precision, though, if I look at this, I can see 4.75, 4.76, 4.74. They all have 4.7 in common. And then this last digit is very, very close. So what that means is this data is precise because they are all close to one another. Okay? Now, something else that we need to note is that if a data value is exactly the same as the accepted value, we say the data is accurate. So, for example, if one of these pieces of data for trial 1, 2, or 3 had have been 3.75, we would have said the whole thing was accurate. Okay? Even if the other ones had been the 4.76, whatever, if you have one data point that is the same as what your actual or accepted is, then you automatically say that it is accurate. Okay, now let's do another problem, and I want you to try this one on your own. So after I get it wrote down, you want to pause the video, take a moment, and work this one out for yourself. So this is very, very similar to the problem that we just did. Okay, so the following measurements were made to determine the density of a material whose value was 1.24 grams per milliliter. Then we have our trial number 1. And then again, we are asked to describe the accuracy and precision of the data. So again, take a moment and pause this video and work this one out yourself. I trust that you have paused the video and that you are now coming back to see if you had this correct or not. First things first, we got to figure out what our actual or accepted value is. And in this case, it is the 1.24. Now, when I'm thinking about accuracy, I'm wanting to see if my numbers are close to this 1.24. Well, they are. They're 1.20, 1.22. So, that means that we are accurate. And then for our precision, all of my data points are really close to one another. In fact, 2 of them are exactly the same. So that means that we are going to be precise as well. Now, last thing that we are going to talk about in this video is going to be something called percent error. So, percent okay, and so percent error, what we can do is we can determine how well an experiment was conducted using the percent error equation. And the percent error equation is that your percent error equals the absolute value of your measured minus your accepted. So remember, accepted is your actual. Divide it by your accepted, and since this is a percent, you have to times all of that by 100. Now, the absolute value, you can do that on your calculator. It's the ABS button. Or, since you know it's absolute value, you know that you can't have a negative number. If you end up with a negative, just ignore the negative sign and make it positive. Either way will work. And just to clarify, that measured is the value gathered from the experiment. Okay. Now, in order to help us out with this and to make things a little bit easier, we use something called the guess method. And the guess method is your given, unknown, equation, substitute, and solve. And yes, you have to show all of these steps for each of your percent error problems. The reason for that is 1, this helps you identify what you actually need from your word problem and what you don't. 2, it keeps everything organized. And 3, it makes you slow down. Because a lot of times you're like, oh, well, I know what to do. I'll just go ahead and plug it in, whatever. And then you end up messing up. So that's the point of the guess method. So we're going to do an example, and we're going to use the guess method for that example. So a measured value for the atomic radius of platinum atoms was determined to be 143 meters. If the Merck index reports 130 meters, what is the percent error? Okay, well first, we've got to start out with our given. And for right now, I'm going to write given beside the G. If you know what it means, then you don't have to. Well, we first need to figure out our measured and our accepted values, because those are the things that we have to have in order to plug into our equation. So the first thing is my measured value. Well, it tells me a measured value and then 143 meters. And then for the accepted, it tells me that there's this Merck index report. So that Merck index report is going to be the thing that all of the scientists have agreed upon, that the value should be 130 meters. So that is going to be our accepted. Okay, so our unknown, or the thing that we are trying to solve for, is going to be our percent error. We don't know what that is. Our equation is going to be that our percent error equals our measured minus our accepted divided by the accepted times 100. And as you can see, I've kind of shortened that down a little bit, and that's okay. You can do that as well. So then we're going to substitute in. So my percent error is going to be 143 minus 130 divided by 130 times 100. And whenever we put this into our calculator and solve, we should get 10% for our answer. Okay, and that is it for our accuracy, our precision, and our percent error.